All right. So just to remind you, last time we proved that if a language is decidable, it can be enumerated in lexicographic order. And if it can be enumerated in lexicographic order, conversely, it's decidable, and we gave the algorithms to do it. Right? If it's decidable, there's a decider for it that says yes or no or yes on every instance. It's always halting, always correct. So you can run the decider as a subroutine after you generate sigma star on the side in a tight loop. All the strings in sigma star come out. That's easy to do in a few lines of code. For each string that comes out, give it to the decider. The decider says yes, you print it out. It says no, you don't. So you are a lexicographic enumerator, therefore, by using it as a decider as a subroutine. And conversely, you can do the opposite. If you have a lexicographic enumeration subroutine for the strings, you can decide any string you want. Take the string, run the enumerator, wait to see if a string comes out of the enumerator that's equal to that string or larger than that string. If it's equal to that string, you say yes. If a string comes out larger than that string, no string will come around anymore that's equal to it because they're coming out in lexicographic order. So you can just say no right there, and then either way you stop and you're a decider. How many get both of these? All right. Hoping it's more than just those who raise their hands, but because we're going to go a lot deeper into this now and prove a very general theorem called Rice's theorem. Anyway, the other pair of theorems, if it's recognizable then you can enumerate it in some order. It doesn't necessarily mean in order that's lexicographic. And conversely, if it can be enumerated in any old order, you can recognize it. How? Run the enumerator. The string comes in the door, match the string against everything that's being enumerated. Eventually, if it comes out in the enumerator, you can say, yes, you'd be right. If it doesn't, you keep running, and you won't be wrong, although you can run forever. But that's okay if you're just trying to recognize, right, and not decide. All right, so having said that, we can prove some more results. So again, this comes out of chapter 4, pages 165, about enumerators and deciders. And so we can prove immediate theorems, easy ones. The finite languages are all decidable. Why? There's a finite automata for each. Finite automata decides yes or no. It's never ambiguous. It never runs forever. In fact, it runs in linear time. So languages that are finite are also decidable. If nothing else, run the finite automata that recognizes it, and now you're a decider. So the regular languages are decidable. The finite languages, which are a subset of the regular language, they're decidable too. The context-free languages are decidable. Why? There's a PDA for each. It says yes or no, each string in the language. So run the PDA, simulate it. Now you're a decider. Now you can say yes or no. You never have to run forever. Okay? How many get those three theorems? All right, good enough. So let me show you why it's hard to decide certain things, even though they seem easy. So the string x cubed plus y cubed plus z cubed is an equation. It's a formula. Take the set of all integers that are representable as a sum of 3 cubes. It's just a set of integers for all x, y, and z. Compute their cubes, add them up, and that's a member of your set. The question is this set infinite? The answer is yes, because it contains all cubes as well as many other non-cubes. Okay. If you ask a slightly more complicated question, is it Turing recognizable? If a string comes along that you're being asked to tell if it's a sum of 3 cubes or not, how can you do it? How can you recognize yes instances? Strings that actually are in that form. Well, have a tight loop, actually a triple loop, iterate over all values of x, y, and z, but do it in dovetailing fashion. Don't run z to infinity and back, before you run x and y a little bit too. So do a dovetailing over x, y, and z. Compute the sum of the 3 cubes. See if it's equal to your string that comes in the door. If it is, you can say yes with definiteness. You'd be right, and you're a recognizer. Now, if the string isn't of that form, you may run for a long time. In fact, you may run forever if it's not in that form, trying all combinations of x, y, and z. You won't be right, but you won't be wrong. You'll just be running forever. But that's okay. You're a recognizer, not a decider. You don't have to stop every time. How many get this? All right. So that set of integers is recognizable. Next question. Is it decidable? can you tell not just the yes instances by trying a lot of combinations, but the no instances also? Because that algorithm won't cut it for the no's, because it could run forever. Answer is nobody knows. It's an open question. If you can solve that one, probably a PhD in mathematics and computer science, both. So a question comes from very simple, whether it says infinite, trivial, to, a little bit subtle. You need an algorithm, dovetail, trial combinations, convince yourself that it works, that's fine. To slightly more complicated, that's actually nobody on earth knows. Another interesting question, is 29 a member of this set? Is 29, the integer 29, an element of this set S? How many say yeah? Sure. Why? Yeah, so what value satisfy it? Why is S an element of this set? 1, 1, and 3. So 3 cubed is 27 plus 1 cubed plus 1 cubed is 29. Okay, simple enough. What if I ask you a slightly more complicated question? Is 30 an element of this set? For that, I won't bother to take a poll because yes, but there's the answer. It's the sum of these 3 cubes. I mean, 2 of them are negative numbers. It's hard to imagine how you'd guess something like that, but brute force before you can run a program, and after a few days of CPU, it may spit out this thing. All right, see how you get from 29 to 30. The order of complexity of the answer was enormous. Is 33 an element of this set? Nobody knows. Nobody on the planet knows the answer to that. Yes or no? Nobody knows. It's amazing. From trivial to complicated to completely unknown in 3 easy steps. So questions can become very, very difficult if you slightly tweak them. So you get used to that idea. In math, it happens all the time. Some theorems are trivial to prove, but if you tweak it slightly, one word changes to some other similar word. Now it's an open question. Okay, so this all goes back to Matiashevitz's solution for Hilbert's 10th problem. I think we mentioned that when we talked about Hilbert's problems, and in particular his 10th problem, and so on. So, undecidable things creep up very quickly on you, before you know it. All right, but before we get into the generalities of it, let's prove a few more relatively simple theorems. So first, the decidable languages, they're closed under union. Remember, we did closure properties for every time we came up with another class of languages in the Chomsky hierarchy. We proved some closure properties, disproved other closure properties. Most of them were proved because they were true. A few were false, so we disproved them. But the decidable languages, they're closed under union. Why? In one sentence, why are the decidable languages closed under union? It's not hard. Yeah. If 2 languages are decidable, you can decide their union, whether it's in one or the other. Just run the decider for one. If it says yes, you're good. If it says no, run the decider for the other. If it says yes, you're good again. If both say no, you're out of luck. You say no also. So you're deciding their union, therefore, by running the 2 decider. You don't even have to do them in parallel. You just run them one after the other. And you don't even have to run the second if the first one says yes. It's already in the union. Right? How many get that? Simple algorithm. We just proved this theorem. All right, so the one word is simulation, basically run the deciders. They're closed under intersection. Now this one should be really easy. So in 5 seconds, somebody come up with an answer. Why are decidable languages closed under intersection? Yeah, it's got to be yes for both deciders. So run the first decider. If it says yes, run the second decider. If it says yes, you say yes. If either one says no, out of luck, you say no too. You're now a decider based on these 2 subroutine deciders. You're a recognizer in intersection. End of story. Next one, they're closed under complement. Again, that's an easy one. Why is a decidable language closed under complementation? Take the strings, make them into non-strings, take the non-strings, make them into strings. In other words, negate the set. Complement the set. Now, if the set was originally decidable, it's still decidable after the complementation operation. Why? convert yeses to noes and noes to yeses. So whatever the decider says, you say the opposite, be contrary. How many get that? All right, so that's decidable too. So decidable languages are closed under complementation. Take a decidable language, complement it, you still get a decidable language back. They're closed under concatenation also. That one's a little bit subtle. You can't just do it immediately. You got to try some things. But there's still a pretty straightforward algorithm. So I give you a language, I tell you it's decidable. Give you another language, that's decidable too. Their concatenation must be decidable. Well, first of all, what is the concatenation of two languages? All strings that do what? Yeah. Take all combinations of strings from the first language, from the second language, bash them together, concatenate together. All possible combinations, throw them all into a big bag. That's your concatenation of the two languages. So why is the concatenation of two languages decidable if the original two languages were decidable too? Yeah. Take the string, partition it into two pieces every which way you can. Like 1 and n, 2 and n minus 1, 1 and n minus 1, 2 and n minus 2, 3 and n minus 3, all the way to n minus 1, 1, and n 0, which is the same as 0n, I guess. Take all combinations of ways to partition a string. For each one of those partitions, in other words, you're unconcatenating, intuitively. You're unconcatenating, you're splitting a string into two pieces. Feed the first piece to the first decider, feed the second piece to the second decider. If both says yes, then you decide also yes. Then you say yes as well. So you are basically saying yes to all ways of concatenating strings, one from every language. Now, if some of those unconcatenations or splits are no's, that's okay. If one of them is a yes, if there's a way to unsplit the string in such a way that both deciders accept the two pieces of the split and both say yes, if there's a way to do that, you're good, you say yes. If the other ways don't work, that's okay. Look for a way to say yes. If there's no way to say yes, if all ways of splitting doesn't work, then and only then you say no. So you, by doing this, are a decider for the concatenation of the original two languages of the other two deciders that you're running as subroutines. Try to say that 3 times fast. How many get this? All right, any questions about this? It's a bit subtle because you got to try a lot of things. It's not just inverting a yes to a no or no to a yes, like in the case of complementation. All right, but you can do this. And by the way, how many ways are there to split a string into two pieces such that their two pieces concatenated together gives you the original string? That's easy also. How many ways to do that? Yeah, it's basically the length of a string, right? You can put the split either before the first character or after the first character or after the second or after the third or after the fourth, and all these will be unique ways of splitting it, and that's pretty much it. Just an aside. I mean, it doesn't change the original argument of how many ways to do it. I just wanted to make sure you understand how many ways to do it. It's not exponential. It's not quadratic. It's okay if it was, but it isn't. So, all right. So you basically guess factor or guess split. Guess a way to split the string that works. Okay. All right. They're closed under clean star. That one is a generalization of the previous one. How can you tell if a decidable language, how could you decide a language that's the clean star of another decidable language? So if a language is decidable, you take the clean closure of it, and the result is also a decidable language, necessarily. It can't go south and you'll become undecidable. Why is that true? And here's the hint. Guess factor the string and simulate. So it's the same strategy as before, except what? What's the difference? Are you splitting it into two pieces? It doesn't have to be with itself. It could be two different things concatenated. Why? Because when you take a clean closure of something, it's not the same copy over and over and over. It can be different copies concatenated together, right? They're independent. Because if you concatenate the language with itself, it's all strings from that language concatenated with all other strings from that language, not necessarily the exact same string every time. It's all possible. It's a cross product. It's all possibilities, but it's a very good try. What else? So you're trying different splits, but what? You want to try two pieces concatenated together? Is the clean closure just two pieces, two strings concatenated together? Could it be three strings? How many can say it can be three strings? 4 strings, 17 strings. Yeah, it can be any number of strings. So what do you got to do as an algorithm to see if it came out from the clean closure? A string comes in the door. You want to see if it's the result of the clean closure of something else. You have a decider for that something else. So you want to unsplit it an arbitrary number of ways. Partition it not just 2 pieces, but 3, 4, 5, 6, all the way up to the entire length of the string pieces. So if the string is 17 long, partition it into 1 and 16, 2 and 15, 3 and 14, and so on. But also partition it into 1, 1 and 15, 1, 2 and 14, 1, 3 and 13, and 2, 1 and 14, and 2, 2 and 13. How many get all this? You got to try all possibilities of partitioning into any number of pieces. What do you do with all these pieces? Run them through the decider, all of them. Make sure the decider says yes on each and every piece. Then that whole string must have arose from the clean closure of that language decided by whatever that decider decides. Whatever the language is, the language of the decider. Okay, so this last one is a generalization of the previous one. The previous one is talking about concatenation, where you just have 2 pieces concatenated together. The clean closure has any number of pieces. So you got to undo the split by splitting it into a lot of different pieces, and all combinations. Now, how many combinations there are of unsplitting a string into lots and lots of all possible pieces? Give me a ballpark. I'm not interested in the exact formula. Yeah. It's exponential. Let's just say it's exponential. It's actually probably more than that, but it's exponential. But that's okay. Even if it is exponential, this still works because this algorithm will terminate. There's only a finite number, even though it's large and exponential. All right, how many get this? Just want to make sure that enough of you get it, because we're going deeper and deeper into this set of concepts. And if you're having trouble now, you're going to have a lot of trouble in 20 minutes. So I want to make sure that you're all comfortable with this. Any questions about this? Yeah. It's not closed, but that's not the reason why. Let me give you an example. First of all, when you mention a phrase like the end of infinity, it makes me a little nervous, because that thing that you mentioned doesn't exist. Right? There's no end to infinity. So I hope that's okay with everybody. We can sort of talk about it informally, but be careful. Secondly, an infinite union doesn't preserve decidability. It doesn't even preserve regularity. How many get that? Infinite union doesn't preserve regularity. Why? In one sentence. Why doesn't infinite union preserve regularity? If you take an infinite number of regular things, all union together, why isn't the result necessarily regular also? What can go awry? How many have seen this question before? Where have you seen it? It is in the problem sets, of course. So some of you must have solved that one, right? It's not hard to solve, but you got to have some insight about it. Let me give you a simpler example. Why doesn't, if you add 2 integers together, you get an integer? How many believe that? Add 2 integers, you get an integer. All right. If you add an infinite number of integers together, do you get an integer? How many say yes? You're right, you don't. An infinite number of 1s added together is not an integer. Because if it was, it would be something more than that, and there isn't, because it's already an infinite number of 1s. So just because an operator preserves some property under a finite number of applications doesn't mean that the same operator preserves the same property under an infinite number of applications. You cannot make that leap. It doesn't even work with addition. Addition of any two integers gives you an integer, but addition of an infinite number of integers is not an integer. In fact, it's hard to even define what that means. All right, back to regular sets. Two regular sets union together is a regular set, sure enough. But an infinite number of regular sets union together is not necessarily regular. Why in one sentence? Go. Yeah, you can create 0 to the n, 1 to the n by unioning together 0, 1. That's a finite language. Fine. 0, 0, 1, 1, finite language. Okay, union that with the first. 0, 0, 0, 1, 1, 1, finite language, regular. Okay, union that with the rest. And by the time you take an infinite number of 0 to the I, 1 to the I, each one separately as its own language, which is finite and therefore regular, you've unioned together an infinite number of regular sets, but the result is 0 to the n, 1 to the n, which is not regular. End of story. How many get this example? And you can do this with lots and lots of things. In fact, you don't even have to do 0 to the n, 1 to the n. You can go the halting problem. I said the halting problem is a bunch of strings. It's a very complicated set of strings of which programs halt, which don't halt, represented as strings. Take each program by itself as a set with one element in it, just that one program. Take another set with the second program, a third set with the third program. All these are languages which are finite because they only have one string each, so therefore they're all regular. Unioning them all together, you get the halting problem. So it's not just not regular, it's not even decidable. So be careful when you apply operators that preserve a certain property from a finite number of applications, and be careful when you try to take the leap to an infinite number of applications, that's all. So I gave you probably a much more general answer that you were expecting, but I want to make sure that's very clear. Does that make sense? You probably forgot your original question. In fact, I probably forgot your original question too, but that's nevertheless all true. Okay, so those were properties of decidable languages. Let's look at properties of recognizable languages. Again, it's almost the same with a couple of startling exceptions. They're close under union. So if something is recognizable and another thing is recognizable, their union is recognizable too. Why? One sentence, go. Parallel simulate. How many see that? 2 words, hits it on the head. Parallel simulation. How many get that? All right. More verbose. What does that mean, parallel simulation? Expand that 2 words into a whole sentence so everybody else can get it. What are you parallel simulating? Somebody else. Let's get more people participating. Same 5 people impressed me greatly, and that's fine, but let's get more people answering questions. The answer is already on the table. Parallel simulate. What does that mean? It's not hard. I mean, the 2 words basically say it, but explain. Yeah. Yeah, except let's get very pedantic about use of words. You said parallel simulate 2 languages. The machines for those languages. Yeah, you can't simulate the language, you can simulate the machine that accepts the language. I just want to make sure that we're good on the semantics. All right, so you have 2 recognizers, one for every language. Both are recognizable languages. That's why they have recognizers. A string comes in the door, you want to see if it's in their union. Well, run both recognizers simultaneously. If one of them says yes, you're good. If both says yes, you're good also. If neither one says yes, in particular, if one of them says no, you keep running the other. If both say no, you're definitely a no. If one says yes, doesn't matter what the other does. The other can run forever. If one says yes, you can stop the other and you're a yes. You can declare yes, declare victory, walk away, you'll be right. If both say no, you have to say no. But if one runs forever and the other runs forever too, or if one says no and the other runs forever also, you're waiting on a yes. You're the union, so you have to see at least one yes from either one of them. You don't care which, it's the union. So if both of them run forever, what do? You're the simulator. You just keep simulating. But that's okay. You don't have to decide. You have to recognize. So if it's a yes string, eventually one of the two will say yes. It's in my language. And then you'd say yes also, and you'd be done. If neither one says yes, either because they say no or they run forever, you can run forever also, and you're not going to say yes, you're not going to say no, but you're not going to say yes. So you won't be right, but you won't be wrong either. You'll be running forever. But that's okay now because you're a recognizer, not a decider, so you don't have to always halt. Running forever as an implicit way of saying no is okay. Like not returning somebody's call or giving them a cold shoulder is a way of rejection. Okay? How many get this? All right, enough. Good. Now, why the word parallel? Why didn't he just say, or she said, simulation? Why is the word parallel important there? Yeah. Yeah, because you don't know if one of them runs forever, and if it does, and you run only that, you'd be running forever too, where if you tried the other, you'd stop very quickly and get your yes. All right, so it's a hedging strategy. You don't want to run forever with the bad apple if the good one will get you there right away. So you have to kind of hedge, and you don't know which is which ahead of time. So you got to hedge your bet and run both. Round robin, time slice, parallel simulation, two parallel threads, however you want to think about it, but you got to do both simultaneously, one way or the other. That's important here. You can't just gloss over that detail and still pretend to understand it because that's a critical detail. Okay. Any questions about that? We just proved a closure property for recognizable languages. Let's just go again. The recognizable languages, they're closed under intersection. Again, in one or two words, how would you prove it? Choose a word carefully. Recognizable languages are closed under intersection. Yeah. Parallel simulation. So that's two words. Can anybody reduce that two-word answer to one word? That's a 50% savings right there on the number of words going from 2 to 1. See, that forces you to think about which one of the, because what he said is right, but think about which one of these two words that he said is more important than the other. Is it the simulation word or is it the parallel word? Think about it. You're going after the intersection. How many understand the issue right now, the question on the table? Okay. What's your answer then? Yeah. Simulation. It's hard to get away from the word simulation because it's doing something that something else does. So that's simulation right there. Now, what about the parallel? Why isn't the parallel so important here for the intersection? Yeah. Yeah, so if one of them runs forever, it's okay for you to run forever too, because that's an implicit rejection. It's intersection, so that means both have to accept. So you can run one, wait for it to accept. If it accepts, fine, you got that one. Run the other one, wait for it to accept. If the second one accepts, good, both accepted. You can say yes and declare victory, and you'd be right, because both accepted. You're in an intersection then, because it's in both. But if one of them says no, you can stop, don't even bother simulating the other one. If one says no, the string is out, because it's not in the intersection. One of them is, it's not there. Because the intersection has to contain it in both. That's why it's called intersection. It's got to be not just in one or the other, it's got to be in one and the other, in both. So it's okay to run one and wait to see what happens. If it runs forever, you run forever too. But that's okay, because it ain't there. And so it's okay to run forever. It's an implicit no. So now you don't have to do it in parallel. But if you did it in parallel, it'll still work, obviously. You just don't have to anymore. Not for this one. Okay, any questions about that one? So we're proving a bunch of theorems in rapid succession. None of them are particularly difficult. It's just you got to keep in mind the big picture. Yeah. Well, don't even think about machines. Think about C code or Java code. You know, you have two subroutines that recognize strings. Say yes or no on each string. Now you want to recognize the union of the sets of strings that both of these subroutines recognize. What should your script code do? Well, take its own input string, run it with one of those subroutines, wait for it to recognize it. If it does, run the second. If it does, say yes, you'll be done, right? So don't even think about them as machines. We already said these Turing machines can do everything that's computable, and so you can think about them as pieces of code now. Of course, you could still think about it strictly as machines. So the Turing machine comes in, a string comes in, it's on its input tape. Make a copy of that string over here, preserve the original copy. So that probably goes more towards your question. How do you preserve that copy so you remember what to give to the second machine when it's supposed to start running? Well, make a copy of it. Run the first machine on a copy of that string. Don't let it touch, that buffer that stores the original string there. That's demarcated on the tape with a $sign between so you don't run it over and overwrite it. The machine will execute on a copy of that string, see what it says. If it says yes, you stop and say yes. Well, you can't stop it. You have to still run the second machine because it's the intersection, not the union. Anyway, you record what it does, and if it says no, you can say no. If it says yes, fine. Then erase everything it did on the tape except that input buffer that still contains the input string that you made a copy of originally to preserve it. Then make another copy of that string and run the second machine on that. That's all. So you don't lose that string between one execution and the next. And it's easy to do. With a Turing machine, it's easy to do with a piece of code. So if you have a subroutine that touches and messes with an array that you give it, and you still want the array intact after it's done, what do? Make a copy of the array before you give it, right? That's all. In real life, you do that too, right? Right? You want to give somebody a photograph, and who knows what they'll do with it, and edit it, and colorize it, and snapshot it, or whatever, and then your photograph will be all embellished, and you won't have your original photograph anymore. So what do to prevent that from happening? It's not a trick question. Maybe you never thought about it this way, but what do to prevent them messing with the photo that you gave them so that you can still preserve the original? Give them a copy. Don't give them the original. That's it. That's what you do in real life, too. Easy. Right? In fact, it wouldn't ever even occur to you to give them your original copy and not keep any copies to yourself. Think about it. Whether it's photographs or other important documents or whatever, you give a photocopy, you give a copy. You don't let somebody mess with the original so that you can preserve it and do other things with it so you don't forget what it was. These machines do the same things at your option. Okay, here's a kicker. The recognizable languages are not closed under complement. All the other ones were closed. The regular languages were closed under complement. The decidable languages were closed under complement because you can change a yes to no and no to yes. Why can't you change a no to a yes and yes to a no here and preserve closure under complementation for the recognizable languages? Yeah. Yeah, if it doesn't end, if it's never ending, you're not sure what to change it to, because never ending means, well, it's an implicit no, but it's only implicitly no. Maybe if you run for a century, it'll become a yes. Maybe if you run for a millennium or a Googleplex years, it'll become a yes eventually. So it's not sure. You're not sure how to interpret that in order to negate it. In other words, you can't make it decidable by force. So again, in real life, it's the same thing. If somebody never returns your phone call or your email, that's not necessarily meaning that you got rejected or ignored. Why in real life? Why doesn't it mean that they're deliberately ignoring you? Maybe email went to the spam. Maybe they never got the email. Maybe some hacker messed with it and stopped it in its tracks. Maybe they never bothered to look at their email for a long time. Some people do that. Who knows? But it's not necessarily that they're dissing you. You just don't know. But for sure, they didn't warmly welcome you back, with some reply. That's what they didn't do. Now, don't necessarily interpret that adversely. It's good advice for real life, too, by the way. People have issues. These machines have issues, too. Right? They're working on it. They don't know what the answer is. They're trying. And it's hard to negate that implicit running for a long time into some negated answer, because you're not sure what it is. You're not sure if it's just a no that will take forever and a day, or maybe it's just a true infinite loop that will never end. Okay, so they're not closed under complementation, and everything we set up to now is not exactly a proof, it's an intuition. Here's a proof that they're not closed under complementation. The halting problem, it's recognizable but not decidable. How many understand that? The halting problem is recognizable. How? Simulated. And if it halts, you'll know. If it doesn't halt, you'll never know, but that's okay, because you're a recognizer. It's okay to run forever along with your simulation. So the halting problem is recognizable, but it's not decidable. If recognizable languages would be closed under complementation, that means that the complement of the halting problem will also be recognizable. How many get that? If that theorem was true, it would be applying to every recognizable languages, not just a specific one. And the halting problem is an example of a recognizable language. So if this theorem towards contradiction was true, if the recognizable languages were closed under complementation, then the complement of a recognizable language must necessarily be also recognizable. In particular, the halting problem complement will be recognizable too. Now show me where the contradiction is. I carried you to 3/4 of the proof. Finish it off. So if the halting problem, which we know is recognizable, and the complement of the halting problem, which by this non-theorem would be recognizable too, where's the contradiction in that? Yeah, so run both recognizers. Run the recognizer for the halting problem and run in parallel the recognizer for the complement of the halting problem. And now you can decide each and every program whether it halts or doesn't halt by seeing which recognizer says yes. And one of them better say yes, because one recognizer says yes for all the halting ones, and one recognizer says yes for all the non-halting ones. And it's exact complements. Their union is all of them. So one of the two recognizers will always flag down the right answer for you. So run them in parallel. Now parallel is important here. And eventually one of them will find the answer for you and says yes, and depending on which one it is, you either say yes or no. It runs forever or it doesn't run forever. And so you're now decided the halting problem. From these two recognizers, you've built a decider for the halting problem, which means the halting problem is not decidable. But we know it isn't decidable. We proved that a long time ago. Turing proved that in 1936, and we proved that a couple of months ago. So there's a contradiction. That's a proof. So the recognizable language cannot be closed under complementation, because if they were, they will all not just be recognizable, they'll all be decidable too. How many get that? Any questions? All right. But they're closed under concatenation. How do you do it? Same as the last slide. You guess factor a string, you split the string. In other words, you unconcatenate, which means split the string. For every split, take two pieces, run them through both recognizers. Both have to recognize for you to recognize the original string. And you have to do it in every possible way to split, i.e. unconcatenate. And there's a linear number of them, as we said earlier. That's okay. Run through all these cases. If both say yes, on one of those cases, you're good. If they say no on some of the cases, that's okay, as long as on one of the cases they both say yes. That means that string must have come from the concatenation of these two recognizes languages. So you're recognizing the concatenation of their respective languages. How many get that? Okay, any questions about that? So that's pretty straightforward, like the last corresponding theorem on the previous slide. And lastly, it's closed under clean closure. Again, there you unconcatenate from the clean closure, you unclean close, I guess. I'm kind of making up a phrase here. But the point is, you look for all ways to split the string into not just two pieces, but to a number of different pieces. And you run all these pieces through the recognizer. And if all say yes, then that string must have come from the clean closure of the language of the recognizer. So now you, the simulator, are recognizing the clean closure of the language of the simulated machine that you're simulating. So recognizable language clean closed gives you another recognizable language. How many get that proof? That's a proof. Okay. Any questions about any of these theorems? We just proved 10 theorems. Just proved 10 theorems in 40 minutes. That's pretty good, 4 minutes a theorem. And, if we keep going like that, we would probably hit 1,000 by the end of the course. Any other questions about this? I mean, none of them are particularly difficult, but you have to wrap your mind about what's going on and see, the main idea for all of these in one word, if you had to say only one word to describe the proof technique for all 10 theorems, what word would you choose? Not a hard question. What word appears the most frequently on these two slides? That's the answer. Simulation. Just run them. Right? So that's a very important concept, is simulation. Do what it does. Whatever it may be. Okay. And sometimes you have to run a parallel simulation, because you don't want to run away forever if what you're simulating runs forever too. You may want to be careful, especially if you simulate multiple things. So that's kind of a secondary concept, is not just simulation, but parallel simulation and dovetail or time slice through the things that you're simulating so that you don't get dragged to infinity along with the poor thing you're simulating that's lost in confusion, rushing towards infinity in itself. If you can avoid being dragged to infinity along with it, that's better. So parallelism helps there. And again, when I say parallelism, I don't mean true parallelism. There's no such thing as simultaneity in this universe, actually. It's a very deep concept from physics. 1905, special theory of relativity, Einstein showed that the concept of simultaneous doesn't really exist. It's something that we invented. The misconception of human thinking. Anyway, similar in computer science. It's not relativity, but the notion of simultaneity is a misnomer, too, about computers. Whenever you have what you think is simultaneous or parallel execution, really could be serialized and done round robin, time sliced, back and forth across the threads or whatever. Okay, I hope you understand that concept. It's a very deep, important, fundamental concept. But sometimes you can't get away from it. You can't just ignore it. Because that concept allows you to not being dragged to infinity along with some erroneous thing that's you're simulating and happens to be stuck in an infinite loop unbeknownst to itself. And because you're simulating it blindly, you'll never know and you'll just be dragged to infinity along with it. That's not a good thing if it could be avoided. Certain scenarios it cannot be avoided. But when it can, avoid it. And now you know how. All right. Now we're going to deeper waters. We're going to generalize all of this, as if this wasn't general and abstract enough already. All right, so we're on page 206 of the book, Mapping Reducibilities. This diagram will come about again and again and again, dozens of times in the next few weeks. So take a look at this diagram very, very carefully. There's a lot of stuff embedded in it, even though it looks pretty simple. By now, you already have an inkling that innocent-looking things can have great depth and subtlety about them. All right. What are reducibilities? So a language is reducible to another language if there is some computable function that maps yes members to yes members and no members to no members from one language to the other. So it maps strings to strings. So here's that image that I warned you about. So A is a language, B is a language. They're both sets. Sets of what? Sets of strings. What's a string? A sequence of characters. So A is a sequence, a set of sequences of characters. A is a language, B is a language too. And F is this mapping. So here's a string W in the language A, and F maps that to some string F of W, and F of W is an element of B. So far, no big deal. It's just kind of normal mapping of some domain to some range according to some function. You've all seen functions before, like f of n is equal to n squared, f of x is equal to sine x, or e to the x, or whatever. Here's a f of w that transforms a string, just like other f's that you've seen before. Functions transform numbers or matrices or vectors or other objects. This one transforms strings. It sends strings to other strings. And right now we're keeping it general. We're not saying exactly what f is, but we're saying it is computable. Because some functions are not computable. We already know that. The halting problem is not computable. F of some program string, such that f is 1 if the program halts, f is 0 if the program doesn't halt, that function is not computable. If it was, it'd be solving the halting problem algorithmically, which we know is not possible. That function still exists. Not computable doesn't mean the function doesn't exist. It means the solution to it as an algorithm doesn't exist. Those are two very different things. How many understand this difference? The function exists sure enough. I just said what the function is. It's 1 on all the programs as strings that halt, and it's 0 elsewhere. I just defined a Boolean function, f. It corresponds to the halting problem function. So the function certainly exists. I just defined it. It's defined completely unambiguously. You know exactly where the zeros and the ones are in the range. What you don't know and what doesn't exist is an algorithm to solve it. That's the issue. Okay, so in general, f maps strings to strings, and it maps them in a way that's constrained. If you have a string that's in the language, W, because W didn't have to be in A. W could have been out here in A's complement. How many get that? So I'm saying W is in A here, but some other V could be outside, and that's okay. But if the string W is in A, F will map it to a string F of W that's in B. In other words, it'll map yes instances, members of A to members of B, and it'll map non-members of A to non-members of B. So it preserves membership from A to B. That's important, actually. You'll see in a minute why it's so important. Right now, you say, okay, fine, I get it. Hear me now, believe me later, okay, that it's important. So that's what F is. It's a function, it's computable. It maps strings to strings in a way that maps members of A to members of B and non-members of A to non-members of B. Now, it doesn't have to do anything else particularly. That's just, these simple constraints, properties of it is what we focus on right now. Yeah. That's a good question. He says, so isn't the cardinality of this set B must be at least as large as A? Interesting question. What do you think the answer to that is? It's a subtle question. Good question. Does B have to be larger than A? How many say yes? How many say no? Kind of a split vote. What do you think? This is all I'm saying, what's on this slide. You know, I'm not saying anything else about F. Yeah. Could be equal to, let me say a bold assertion. Could be much smaller than. B could be much smaller than A. How? Yeah, we never said there's no collision in B, that two different W's can't map to the same F of W here. So a lot of different things here can map to the same thing there. That's okay. And you've seen functions that create collisions. You know, give me an arithmetic function on integers that creates collisions, that two different things fed to it could yield the same answer. Yeah. X squared. So if you square 2 or you square minus 2, you get 4. So you get a collision in the range. That's okay. So what we're saying is not 1 to 1. That's okay. But that's a good question, and there's your answer. Any other questions so far? This could happen. All right. So it's called a reduction of A to B, and it's denoted by this little symbol less than or equal to, but don't be confused. This isn't the less than or equal to for numbers that we know and love. The equality less than or equal to arithmetic number notion of less than or equal to. It's kind of an overloaded version of that symbol. We use the same symbol, but it means A reduces to B. It's a reduction of A to B, which means exactly what the definition says. That's what the meaning of that. There's a function from A to B that has this property. It's computable, and it maps yeses to yeses and nos to nos. It preserves membership. Okay? Intuitively, what it means is that A is no harder than B. Okay? And you'll see in a minute where all this is going. Right now, it looks like a few simple but curious definitions. Very quickly, you'll see how this blooms into a whole theory of computability, and including NP-completeness eventually, right on the bedrock of this definition. Okay. All right, here's our first theorem. If A reduces to B and B is decidable, A must be decidable also. It has no choice. How do we get such an elaborate theorem simple from this straightforward, innocent-looking, simple definition? Can somebody want to explain that? So there's a mapping from A to B, F, that takes members of A to members of B and non-members of A to non-members of B, and we're saying that B is decidable. Automatically, that means that A must be decidable too. How do we make this gigantic leap of logic here? It's not that gigantic, but yeah. Well, decidable, it can't map everything. It has to map members to members and non-members to non-members. So let's put it this way. If A reduces to B, there's some way of mapping elements of A to elements of B. Let's say you don't know what the answer to A is, or an algorithm for A, but you know an algorithm for B. And you're trying to determine membership in A, but you don't know how. But you know how to determine membership for B, because B is decidable. Okay. So if B is decidable, you can tell membership for B somehow algorithmically. You can exploit it as a subroutine to determine membership for A. How? Take the element of A which you don't know the answer to, because you don't know how to decide membership in A, whether it's in or out of the language. Right? But you know how to decide membership of B in B, and you know how to compute F, because F is computable, so it's an algorithm for F. So take that element W that's in A, you're trying to determine membership for, you don't know how to do it. So what you do is you hit it with F. F is computable, so very quickly you'll get F of that element, F of W. And F of W is in B because it maps members to members and non-members to non-members. So if W is in A, it'll map to an element of B. If W is not in A, it'll map to a non-element of B, an element outside of B. But you already know, by assumption, of how to compute membership in B. Why? Because B is decidable. There's a decider for it. So now you run the decider for B, you run it on F of W, on the mapping of W into this second language B. And in B, you know how to decide membership. So decide the membership of F of W in B. And if F of W is a member of B according to your decider for B, you know automatically that W was a member of A. If F of W is not a member of B, you know automatically that that W was not a member of A. Why? Because F preserves membership. So members become members, non-members become non-members in the other. Now you see why it's important that membership is preserved. So what have we done? We exploited the decider for B to build a decider for A from it. How? By transforming the element into this other space, deciding it there, and then knowing the answer back home, because members remain members and non-members remain non-members. So if across this divide, it remained a member here, it must have been a member there, and vice versa. If it wasn't a member across this chasm, then it wasn't a member to begin with, because F preserves membership. That's why it's important that it does preserve membership. So that a membership tester here will give you the exact same answers as membership tests on the other side. So you've exploited the membership tester, the decider for B, to build a decider for A from it. In other words, A became decidable based on the decider for B and this function that preserves membership. In other words, you transformed the problem. The problem looked like a problem of type A. All of a sudden, you have a problem of type B. And if you can solve that, you're solving A in disguise. How many get all this? It's abstract, but you do this all the time. It's called a reduction. Let me give you an example for everyday life. In fact, all of you are participating right now in this type of reduction in your personal lives. Can anybody think of an example? What am I talking about? I can give you 10 different examples, but give me one. You could, but instead of talking about the objects, let's talk about the strategy. What problem are we trying to solve, all of us here? And what other problem you're solving instead in order to solve the first one in disguise? This is abstract, but I want you to pin it down to reality real tight to show you that this is not just pie in the sky. You're all doing this every day of your lives, every minute of every day. Yeah. Yeah. So how do you, let's say your goal is to become a better programmer. And it's not clear how to do that, but instead transform that goal into studying theory and be able to wrap your mind around abstractions and all sorts of mathematical and abstract ideas. And eventually they'll help you become a better programmer, in fact, a better thinker in general. Let me give you an even more mundane example. Why do you even want to become a better programmer? You know, maybe your parents had this conversation with you one day. You have to pick a job that'll make you a good living, and poetry or art or some other field like that may not be a great career opportunity, even though it's a nice hobby. So study programming or study computer science or engineering in general so that you can have a nice living, make some money, support yourself and one day your family, and so on and so on. So you're all trying to get good jobs or, more generally, have better lives, right? Because if you don't have any money, that's not a great life. You'll be living under a bridge somewhere, right? You have troubles every single day. So you want to be able to buy a home and get the food and clothes and entertainment that you like and need, and on and on and on. So that's the problem you're trying to solve, to be happier in your lives. It's not clear how to solve that problem right as it stands. How do you become happier in your lives? Well, that's a complicated, abstract, philosophical problem. It's not clear what the algorithm for that is. But you transform that problem into another problem that's easier to solve, and then you solve it. And while solving it, the original one gets solved too in some way. What do you transform the problem of making a good living into? In the case of all of you, because you're right here. Get a good education. Get a significant sought-after degree, something that's useful to the rest of society. Once you do that, society will come running, beating a path to your door saying, I'll give you lots of money if you help us in this way, because you have all this knowledge of how to program and how to create hardware and software and algorithms, blah, blah, blah. And that's an easier problem to solve. So it's not clear how to become happier, but it's clear how to get a degree. I'm not saying it's easy. I'm saying you got to, sit on your butts and study for 4 years and pass all these exams and solve lots of problems and on and on, but it's doable. The prescription for that is pretty straightforward. Take these courses, study hard, get good grades, and eventually you get the degree. And with that degree, you'll be able to have a better life because you'll make more money, higher salary, good standard of living. You'll be happier. You won't scrounge for food and shelter every day like a homeless person. Okay. So we've transformed the problem of having a better life to the problem of getting a degree in some engineering field. Now, I'm not saying that's the only way to have a better life. I'm saying it's a way of having a better life. Other ways could work too, and there's plenty of ways that don't work, believe you me. Okay? So, you transform the problem A of having a better life to the problem B of getting a good education. And here you all are engaging in this transformation. You all executed the function F. What is the function F, by the way, in your case, in real life, in this example? What does f do? So again, it's a little bit abstract, but how do you transform? What is the actual transformation process? Just so we're all on the same page. How many understand this example, by the way, just abstractly? Okay. How many can tell me what f is in this example? You've all done this. Yeah. It's basically the time and effort that you put into studying and passing the exams, and even backing up from that, F is the process of enrolling in school, applying for your admission into this university and on. It's the whole thing. From applying to admission to getting accepted to studying real hard, blah, blah, blah. And finally, if you solve that, you're solving some aspect of the original problem A. Okay. Any questions about this example? It's called a transformation or a reduction. You've reduced the problem of having a better life to the problem of getting a degree in a significant field that society cares about. Okay. Any questions about this example and why it's exactly like this picture in an abstract sense? Because that will help you understand this picture. But you see how general this picture is now. You're beginning to get it. It's not just an innocent little picture with two ovals and an arrow between it. It's what you're doing in your lives right now, this picture, in an abstract sense. It's reducing a problem to another problem and solving it in order to solve the original through some transformation. It's transforming or changing a problem into another problem and solving the second transformed problem as a way to solving the original problem. Okay. I hope you begin to see how deep and ubiquitous this thing is. This is just the beginning. Okay. So we show that if B is decidable, then so is A. And in the example of real life, if getting a degree is doable, then having a better life is doable too. That's what that means. How many get that? Okay. Because a degree will get you a better life, whatever that means. At least you'll make a decent living. A lot of it, the rest is up to you. But you can have a decent living and still not have a great life, but you have to make a lot of mistakes for that to happen. Okay, so let's prove the converse. So here's the second theorem. If A reduces to B and A is not decidable, then B is not decidable either. First, let's prove it in the abstract. Let's pin it down to this example from real life about an education and a better life. So first, let's do the abstract. If A reduces to B and A is undecidable, there's no algorithm for it, then there can't be an algorithm for B either. Why? Because if there was an algorithm for membership in B, and F is computable, then in order to solve A, in other words, to have an algorithm for A, you don't know how to solve it directly, but you know how to transform it to B, and then if B was decidable, then you'd solve it in B, and therefore you'll have the answer for A, because it maps members to members and non-members to non-members. It maps successes to successes and failures to failures. Okay? So if B was decidable, A must be decidable, and if A is undecidable, B must be undecidable too. Okay, you can't have A be undecidable and B remain decidable, because if B is decidable, you'd solve A by virtue of mapping it to B, solving it there, and then you know the answer for A, which means A is decidable, but A is undecidable. So B can't be decidable either. How many get this logic? Okay. Now what's the example from real life? Let's say that for sure, if you have a good living, if you have a good income or whatever, a good job, good salary, good career, good income, you'd have a better life. Okay. Let's take that as an axiom. I'm not saying that's necessarily always the case, but let's just take that axiomatically. Well, that means that if you can't have a better life for whatever reasons, that means you can't have a good income either. Because if you had a good income, you'd have a better life. All right, that's the example from real life kind of application of this theorem. But let's prove all this. Let's prove the theorem, the second theorem, even more simply than all of that. Can anybody prove the second theorem basically right on the back of the first theorem, right on the basis of the first theorem. Do it in one word. Tell you what. What do you say? Yeah. For those who didn't hear him, what's that magic word? One word? So I'm asking again, knowing that maybe some people didn't hear you, so they have to regurgitate what you just said. What's the one word that says it? Contrapositive. Now we say it proud and loud. Yeah, contrapositive. So the second one is the contrapositive of the first. Right? So if A, let's not say A because A is, if P implies Q, then what can you tell me right away about P and Q? The contrapositive situation. If P implies Q, then not Q implies not P. So, for example, in life, if it rains, the ground is wet. Well, that means if the ground is not wet, it's not raining. I'm talking about the outdoor ground. Right? So it's a contrapositive. So you don't even have to prove the second one from scratch, although we did. We can just prove it by saying it's a contrapositive of the first. It's implicit in the first. How many get that? Okay. So we proved it two different ways now. One the hard way, one the easy way. That's okay. It's a good day when you can do two proofs on one thing, that look different. That means you understand it better. Just be careful about which direction you're mapping, because most of you will probably make this mistake, just like most of you will make type errors and have made type errors. Most of you will make the following mistakes, so be very careful. I'm showing you where a landmine is right now. Be careful which direction you're going in this reduction. Make sure that this is really reducing A to B and not B to A, because they're not the same thing. B may also be reducible to A separately as a separate matter, but it doesn't have to be, and you don't have to do it, and sometimes it may not even be doable, because that backwards mapping may not even exist. So be careful which direction you're reducing to. So again, for real life, don't confuse the notion that in order to have a better life, getting an education will suffice. Because the opposite way is not necessarily true. To get an education, it's not enough to have a good life. That won't get you educated necessarily. Education involves a lot of hard work and studying and wrapping your mind around things and become a better problem solving, rewiring your brain, learn to think rationally and logically and eloquently and so on. That's what an education is. Okay, and one is not the same as the other, although they're related according to this mapping. Getting an education will help you get a better life, but having a better life doesn't automatically get you a good education without all that hard work and extra things we talked about. So it's not a two-way street necessarily. It could be, but it doesn't have to be, depending on the situation. All right. Here's a reduction. The halting problem, we know it's undecidable. There's no algorithm for it. Let's take a simpler version of the halting problem. Not the halting problem on arbitrary strings, but the halting problem on the empty string in particular. Does a Turing machine or a program halt when you feed it the empty string? Maybe that's easy. Because you're not running it on arbitrary things, you're just running it on one thing, the empty string, but you're going across all possible programs or algorithms or Turing machines. Why is that undecidable? And it is undecidable. All right, so why is the halting problem on empty string undecidable? So we'll reduce it from the halting problem. What we're saying, if it's an arbitrary Turing machine and an input string, construct another Turing machine, M prime, that if it ran on its input X, it would do the following. We're not running it, we're constructing it. We're compiling it together. We're not running it, actually. But here's what it would do if you ran it, but you're not running it. But here's what this program would do if it ran. It would overwrite its input with this W. That's the parameter to the original problem, right? So arbitrary Turing machine, arbitrary string W come in. You construct a new machine that would have W built into its finite control. It would write that on the string, the W. It would write that on its tape as a string, and then simulate internally M on that string W, and then it would basically do what M does on that W. If M accepts W, it would accept. If M rejects W, it would reject. If M runs forever, it would run forever, and so on. But that's what it does. Okay, so here's that new machine M prime sort of denoted diagrammatically or pictorially. It takes its input X, because everything has an input. We call it X, that's a parameter. But it ignores its own input, and instead it runs M and W, and M and W are built into M prime. In other words, they're hard-coded as constants in this MW. M and W were arbitrary machine and a string, or arbitrary piece of code and arbitrary input. But once they come in the door, they're no longer arbitrary. We have them in our little hands, and we basically construct this machine that does what I described on M and W are built into it, hard-coded into it as constants. And then it just does it. Now, we're not running M prime. Again, I'll say it 5 more times. M prime is not being run, it's being constructed. So here's what's happening. A machine and a string come in the door. Sounds like the beginning of a bad joke, right? Machine and a string walk into a bar, and you can actually invert it even, so it's kind of palindromic. So arbitrary instance of the halting problem, a machine and a string. Right? So we want to know what this machine does on this string, what this program does on this input. We don't know, but we're trying to find out. We're trying to solve the halting problem. We know we can't solve the halting problem, but here's how we could solve the halting problem if we had some black box that solves this restricted version of the halting problem on the empty string. Let's say some person here is an oracle, a black box, somebody who can solve the halting problem on the empty string. We want to solve the halting problem on an arbitrary string. How do we do it? We take this machine and this string come in the door, this program and this input. We compile it into this new machine called M prime that does what's in the purple box. We're not running that purple box. We're going to feed it to this oracle who supposedly can tell us what an arbitrary program will do on the empty string. And here it is. He's going to tell me what this machine will do on its empty string. And is your answer yes or no? Pick one. Okay, so he says yes. He says yes, this will halt on the empty string. Well, this will halt on the empty string if and only if M halts on W over here. And so if he says yes, I know that M has to halt on W, otherwise this machine will not halt on the empty string. And he told me that it does, and he's an oracle, he's always right. So I exploited him into solving the halting problem for me with this transformation or reduction. Now Nathan has a very good way of describing this using a clip from MacGyver. And maybe at some point he will during maybe Monday night session or some other time. But this basically is what it is. I'm transforming one problem into another. The problem of solving an arbitrary Turing machine or program on the empty string, and I've transformed the problem of solving the halting problem on an arbitrary string into the problem of solving the halting problem on a particular string, the empty string. So that basically means is because the halting problem is not solvable, his problem that he's supposedly solving is not solvable either, because if it was, I'd be exploiting him into solving the halting problem for me, which I know can't happen because there's no algorithm for it. It's undecidable, it's unsolvable. So there's no algorithm for his problem either, and his problem is a simpler one. What an arbitrary machine does on the empty string, okay? And here I'm emphasizing that we're not running M prime. We're compiling it and then feeding it to the oracle, and the oracle is supposed to tell somehow. The oracle may or may not run it, it's up to them. We don't want to make that assumption of what the oracle does or doesn't do, just that it's always right. And next time we'll pick up on this and we'll generalize it into Rice's theorem. And if you think this is abstract, you haven't seen nothing yet. So read the chapter in the book that describes this, please.